Welcome to lecture 15. In this lecture, we will continue the discussion on amortized analysis. We will talk about the remaining two methods, the accounting method and the potential method. So let's start. So for accounting method, it is related to the concept of putting money into the bank in real life. So in real life, a bank account allows us to save our excess money so that we can use this money in the future when we need. And in the accounting method, we will imagine that each operation has an associated amortized cost, and if we perform each operation, we are going to pay such an amortized cost. Now, in case the amortized cost is greater than or equal to the actual cost, so we will have an example soon. So if we are going to pay this fixed amount called amortized cost for each operation, but it turns out that actually we do not need that much to pay what we are going to run for the current operation, then in that case, we have some money left. So there will be excess and we are going to save the excess to the bank. On the other hand, if the amortized cost is less than the actual cost, then the amortized cost cannot pay all the actual costs. What we are going to do here is we are going to use the bank savings to help to pay for the actual cost now. And the key, or actually the only requirement for the design of amortized cost is we want to make sure that for any sequence of operations, the sum of amortized cost is always greater than or equal to the sum of the actual cost. Because in such a case, then for any sequence of operations, this is the total amortized cost as we hope for, can be an upper bound of the total actual cost that we are actually spending. And for accounting method, our goal is to design amortized cost scheme so that the bank always has enough money to pay for the actual cost if needed. Now, if this is the case, the bank always have enough to pay, then in that case, it turns out that the sum of amortized costs will always be greater than or equal to the sum of the actual cost. So this will be satisfied. This is what we need. So let us revisit the superstack problem. And we are going to use the following amortized cost scheme. So for every push operation, we are going to pay for a fixed $2 amount as the amortized cost, while for pop or super pop, we don't care about how many items are there inside the stack. We always pay for $1 as the amortized cost. Now, when a push operation is performed, then the actual cost is actually 1 because we are just pushing an item. So let's say the cost is equal to 1. But we are spending or we are paying for $2 for the amortized cost. So amortized cost is more. So in that case, we have an excess of $1. So this excess of $1 can be saved in the bank. Or, better still, we can try to associate the excess amount of money or this excess of $1 to the item being pushed so that we can later have an easier understanding of what is going on. So this corner is a reminder of every push we pay for $2, every pop or super pop we pay for $1. So from the beginning, we have an empty stack. Let's say we perform a push. So when we push it, we are giving out $2 for this amortized cost. $1 is paid for pushing the item here, and $1 is saved in the bank as the excess. So we are putting this dollar side by side with this item. So when then the next item is also pushed here, then in that case, $1 is spent on pushing the item, and then we have an excess of $1 here associated with this item. So what does that mean? It means that inside this stack, if ever there is an item, there will be an associated excess of $1 here. Now, consider what happens when pop or super pop is performed. Now, when pop or super pop is performed, we are going to use the associated of excess of this $1 for each removed item to pay for the removal of this item from the stack. So precisely, during a pop or super pop operation, suppose that there are k items being removed. Now the actual cost will be equal to 1 plus the number of removed items. So this is the actual cost, right? So 1, we can pay this 1 by using the amortized cost of this $1 to pay for it. And then the number of removed items is equal to k. Yeah, this k is being paid by each of the excess of this removed item. So altogether there are k dollars in these items. So we are using these k dollars of excess to pay for this k. So in that case, what does that mean? It means that we will always have enough money to pay for this super stack and super pop or pop operation. And in that case, we're done. So that's very easy, right? Okay, now let us also look at the binary counter problem again. So here, what we are going to do here is we are going to set the amortized cost for each increment operation as $2. Now, let's consider what happens when the first increment is performed. Now, when the first increment is performed, this was the counter, all zeros from the beginning. It is changed to 00001, something like this. So there is actually a bit being flipped. So the actual cost is equal to 1. But we are paying for $2 as the amortized cost. So what does that mean? It means that we can use $1 from this amortized cost to pay for the actual cost, and then the remaining $1 is saved into the bank. Now again, we can try to understand better about the money in the bank by associating the excess of $1 to the bit 1 inside the counter. So this is a bit 1 inside the counter. Now in general, later we will see that each of the excess in the bank will be associated to a bit 1 inside the counter. Now, so we have seen what happens in the first increment, but let's see what happens for a general increment operation. Now, suppose that during an increment operation, altogether k bits are being flipped. Now, when we are flipping k bits, actually we will understand that which k bits are actually flipped. It must be flipping the rightmost k minus 1 bits, all of them changing from 1 to 0, and then the rightmost kth bit changing from 0 to 1. So we have an example that we have seen before. This is a counter for the value of 5. When it is changed to a counter of value of 6, altogether 2 bits are flipped. So these 2 bits, it is actually coming from a sequence of bit 1, starting from the right hand side, being flipped to all zeros, and after that, the last bit here changes from 0 into 1. So what we are going to do, okay, so for these operations, because k bits are flipped, then we are going to use the excess of each of bit 1 to pay for the flipping that makes it back, change it back to 0. So what does that mean? Okay, so here, let's see, in the actual scenario, when we have the counter value for 5, we would have $1 over this bit 1, and then $1 over this bit 1. Each one has an associated excess of $1. So when it is incremented, this bit changes from 1 to 0. So when it changes from 1 to 0, we pay it by using the associated excess. So it means that whenever it is changing from 1 to 0, we don't care, because there is always a money to pay for it. On the other hand, for the last bit that is not changing from 1 to 0, it is changing from 0 to 1, we are going to do the opposite. We are going to use the the amortized cost of $2 here, this is the first time that we are using the amortized cost, $1 to pay for the flipping of 0 into 1, and the remaining $1 is saved over this bit 1 now, so that it can pay for the later flipping of this 1 back to 0. So in that sense, altogether in this round of operation, we just need to pay for an amortized cost of $2, and then we can maintain the invariant that each of this bit 1 in the resulting counter will have an associated excess. And then the operation can all be paid without any problem. So we will always have enough to pay. And because of this, this is also done. So in this example, we have proven that for the binary counter problem, each of these increment operation will have an amortized cost of 2.